Welcome, Connor.
Thank you for that introduction. I'll try and live up to it. So as you've heard, my name is Connor Jones. I'm currently a Ph.D. candidate at Lakehead University. I'm going to introduce some of the work that I've been working on, as well as the project that hopefully will blossom into a dissertation. So it is the Integrated Forest Modeling System. So the introduction for it, the goal and sort of some of the background of what led to its creation is we're trying to find and create a tool within the modeling sphere that is able to sort of determine how future forest composition will be impacted and affected by not only silvicultural treatments that are being applied on the land, but as well as climate change. So these are two very topical concerns that are coming up. So we're also setting out to try and address some emerging challenges, and I'm sure many here who are involved in forestry as well as timber production are aware and can recognize some of these. So the first that we're seeing is the silviculture practices, specifically how to apply and use new techniques, especially when we're not sure what the outcome will end up being. Along with that is how do you investigate new directions such as management zoning and a daunting phrase such as intensive silviculture. So these are new things that are being added into the toolbox for our foresters to use on the landscape, but we want to know kind of directly how that'll impact our forests. After that is our big word of the day, sort of the more challenging one is climate change. And this is something that we're confronting not only globally, but right here at home in the province of Ontario. One of the challenges with it, not only do we see precipitation and temperature changes, but it's not uniform across this land either. So you end up with some areas receiving more precipitation and others receiving reductions in precipitation and even significant events such as drought. So we want to be able to address that as well. And finally, with this tool, we're playing with the structure here to try and investigate more management decisions, to sort of put that power back into the hands of people to investigate how new directions with policy management and concerns are addressed. So one that has recently come up and is newer in the sphere is ecological considerations. So a lot of this is our wildlife and habitat, but also things more near and dear, such as our wetlands and water systems. And a lot of what is already being touched on at the symposium so far have been results coming out of the COP15 and COP28 seminars and sessions. The big one that we're aiming for is this 30% by 2030. So in order to try and investigate all of these, which is a very large overarching task to do, we set up both our modeling system as well as paired it with some field experiments. So I'll go through why we're trying to do it in tandem. So the first is the rapid change. I'm sure many of you are aware of the IPCC reports. For those of you who are not, it was a multinational conference that sat down and discussed at the table what it is we're facing and ultimately what it is we've kind of done to the planet. And as a result, they came up with a series of scenarios. Many work, hundreds of researchers were involved in it to try and determine what it is we've directly done to our climate and how it will change. So they ended up coming up with a nice term, RCP, which is a fancy way of phrasing what the temperature, greenhouse gas, and precipitation might end up doing. So the challenge with looking at this specifically in a field experiment is these are constantly updated. A lot of it, again, is based off of projections, based off of our greenhouse gas emissions, but as well as other complex modeling software. And as each year turns, we receive new data which further informs these models and kind of gives us more values to look at. So with all of these projections constantly changing, it sort of becomes impractical to set up a field experiment to encompass all of these different scenarios that they've created. But as well as, again, as I've mentioned, the precipitation and the temperature changes in order to do on a land-based field experiment is a daunting task. So one of the other reasons why we're approaching it with a model use as well as timescale. As everybody here has spent time on the land, you could appreciate how long it takes for a tree to actually grow up in our forests to sort of bounce back. Involved in this as well is once you impose a change on the forested landscape, it'll take you a significant amount of time until you're actually able to collect meaningful data which shows you a change and a departure from what is otherwise the norm. So for this reason, we're able to compress and condense a lot of this time through modeling, where decades, even hundreds of years, can be basically squeezed down to a matter of minutes or hours. If it's more complex, days, which is very frustrating, but it's still better than waiting 60 years. Lastly, we also have the concern about our spatial scale. So these changes occur, again, all over the province of Ontario, as well as at these large frequencies of time. And in order to sort of collate all this data, do the number crunching, I like to call here on paper, again, is not only a very daunting task and will make any grad student run for the hills, but it's also very time consuming. Where we can do it in a modeling space, again, really in a fraction of the time, and at, I would like to say, a much higher certainty with less human error involved. So sort of the general structure here, sort of the top-down look at what this model does for you. So we start off in the top left corner here. This is our forest, our stands, representative of the land that we love, hold and love dearly. It's represented in the way that we're approaching it and what we're using in FRI data. So combined with this data, we take historical climate data from a lot of monitoring stations across the country, and we combine it with a lot of the management plans that have already been drafted. Together, we're able to make sort of a digital reconstruction of what the forested landscape looks like in our modeling sphere here. So we take all these inputs and we crunch it all together into the integrated forest modeling system. Ultimately, what this modeling system does for us is it shows us what growth will look like, relatively based off of not only our standing historical data, but as well as some of the new climate data that we're able to introduce based off of those RCP reports for temperature and precipitation. And we're also able to manipulate our management scenarios here and explore those new and innovative techniques that are on the landscape. And ultimately, what we're looking for at the end of the model and what we'll get coming out of it includes the future projected composition of this forest. So what species will do well, what species might decline a bit, and then relatively what their abundance with each other will look like. And then another value that I'm most keenly interested in will end up being our biomass at the end of the day. Biomass is useful for a lot of downstream analysis as well, but in large summary, between composition and biomass, you're able to get a very good picture of the forest. So some of the scenarios that we're running through, especially with the climate here, so the baseline. This is ultimately the one that we're going to be using as our standard to test our other scenarios against. So this is representative of climate from 1980 to 2010. It's supposed to reflect small changes from pre-industrial conditions. And again, it really provides that baseline comparison and what we would expect the forest to look like had we not changed the climate the way that it's projected to change. So then we look into the scenarios that the IPCC have released. They range in severity. It boils down to the changes in CO2 in the atmosphere, temperatures that we're expecting, both in ambient air temperature, and then as well as precipitation changes that will occur across the landscape. I won't read through all of this, but in summary, they kind of boil down to what changes and actions we as a society are willing to take on, and then especially what policies the government are willing to sort of enact here. So some of the management scenarios, we've set the model up to run through to give us an idea of how it can interact. The first is business as usual. So this is assuming that all of the prescriptions that are currently written in our management plans go ahead as planned, and we test to see what they'll look like in 60 years, 100 years, 140 years, at the end of one rotation or multiple rotations. The next one is our full sustainable harvest, sort of trying to, I'll call it, test the system to check for a breaking point, or if all of the available harvested area that these companies and the licenses were allowed to cut were fully harvested, and ultimately what that'll look like. And then the last, which I, again, am very interested in and excited for, is trying to hit that target of 30% conservation by 2030. Now, in trying to construct this for broad acceptance, we're looking at sort of a hybrid model where we're allocating additional land on the landscape towards conservation to hit that 30% target, and then to offset some of that land that is now being allocated to conservation, we're looking at implementing different zoning. So this goes back to our intensive forestry and zoning protocols for it. So an example of what intensive silviculture will look like, based off of some papers that were published as one of the members on our team, is our arboreal mixed wood. So again, this is sort of that intensive silviculture mixture. So it's primarily our aspen and spruce. So the idea behind this lends off of the notion that the whole outweighs the sum of its parts. So we've been able to see that when these two species are combined or are allowed to grow with each other, we actually end up with a larger yield rather than if we had just maintained a monoculture. Now, the silvicultural approach to try and take advantage of this is to leave some of the aspen canopy actually within the spruce itself to allow it to grow and foster the spruce. And then we end up coming through at about 40 to 50 years of age for this stand, and we harvest out our aspen, leaving our spruce canopy behind to grow on its own. And then at about 70 to 100 years, we come through and then we harvest the rest of it. So there's actually a trial of this that is being developed. Again, part of our part of the field experiment network that's being established for it. So on the left here, this picture shows us the bounce back of a stand after the harvest only. So this is representative of extensive forestry, where essentially the only thing that was done to the stand was we came in, we cut it down, and then we left it to do its thing afterwards. As you can see, there's been a lot of grow back. Specifically, there's a lot of aspen mixed in here, and it's very, very dense, which can limit some of the spruce grow back, but it doesn't allow for a lot of space. Now, in contrast, we look at a more intimate mixture here, which is our intensive mixture. Now, I'm sure there's a bit of a striking difference between the two images here, where the one on the left actually experienced some more tending practices for the stand. So some thinning took place in the stand. I believe it was 10 years afterwards. Don't directly quote me on that. But it allowed for the spruce to actually be released from a lot of the aspen cover and allowed for a lot more light to penetrate into the stand and really open it up here. So the scenarios that we'll be running through, it's sort of a grid here for visual reasons. We're going to be assessing, again, our three management sort of scenarios and setups here against our climate change scenarios to try and identify and really hone in on how these stands will respond and react. So some of the outcomes, again, that we're looking forward to coming out of this. The first is our forest composition. So this is our species abundance, the age, as well as the distribution on the land, as well as our biomass. It will also be passed along down for additional analysis, but from this we're able to examine things like the quantity and quality of wood fiber, which is particularly very important if that is your industry and what you're looking to assume. Now, the outcomes from this, again with that biomass, we'll be using additional models to estimate other parameters and examine co-benefits. So these, again, are those additional services that we know our forests are able to provide. Things like our wildlife habitat, our water quality, things like soil erosion protection, really all the benefits that we're able to desire from our forests, we're hoping to try and test and tease out here. A big one, especially as I heard the panel talking about, and some of the other discussions leading how climate change can be addressed and some solutions to it, is looking at carbon sequestration and storage. So sort of the practicality of relying on our forests to absorb a lot of this CO2 and emissions that we have left in the atmosphere. Another big one that has come out of this and will be applied with additional models is fire management. So with the biomass, we'll be able to produce maps on the landscape, such as this, which show us concentrations of not only our species, but biomass on the landscape, which will allow us to apply it for things such as fire management planning and zones of concern. So where a lot of those fuels are located in areas that might be more prone to these disturbances. So this is an example of work that was done in Quebec, Boulanger 2021. So this paper, similar to what we're hoping to do here for Ontario, examined the different climate scenarios. And as you can see at the top there, it gives you the year breakdown of those periods that they examined. And this specifically is for black spruce. So I'm not sure if you can make out some of the values on the line down here, but that red coloration and the orange coloration actually show a decline in biomass that is expected on the landscape. And this is for periods that are really not too far out in the future for us. So most starkly contrasted is 2071, which hopefully, knock on wood, I will live to see the day. But it does not bode very well for us, but more so for black spruce that will experience that decline. So as we've been developing this project, David and Isabel have been very generous with their time and have provided some input for us. Specifically, this is related to the different scenarios that we're wanting to test the model with and sort of incorporate to investigate further. So a lot of this is boiled down to the conservation by 2030. And as expressed, the interest is in mostly protecting the wetlands. A lot of that is value for water quality as well as moose habitat. And it also breaks down into, as we've heard again, reduction in herbicide use, which is something I'm still working on, but have an idea of how we can actually represent that within our modeling. But ultimately, what I'm hoping for, since we have a large collection of knowledgeable people here today, is that we can gain some further insight and further suggestions of things that we can test within this modeling sphere. So as a result of that, there is a survey at the end. But I would like to thank not only my committee, who've been supportive throughout this whole process, but as well to administrative partners with CIF-SEEK, as well as Isabel and David for inviting me to this seminar and a chance to speak with you all, as well as others who have been intricately involved in the development of the project and helping to fund this journey along the way. So thank you for your time. I apologize that I was quick, but hopefully you got an idea of what we're working on here. Thank you.